As we've discussed several times before, we often have to deal with high-dimensional data where the data itself has or appears to have fewer degrees of freedom than the form in which the data is captured. These two, the degrees of freedom and the format of the data, the dimensionality of each is sometimes known as the intrinsic dimensionality, that's how many degrees of freedom the data really has, and the extrinsic dimensionality, which is the dimensionality of the form in which we capture it. In trivial cases, it may well be that many of the feature dimensions are just not important at all, and we can discard them. This is the feature selection process we discussed a few weeks back. But quite often we find ourselves in situations where all of the many extrinsic dimensions participate in the lower dimensional behavior, but just in constrained ways. All the different features do not vary independently, but they do vary meaningfully. Dimensionality reduction techniques attempt to map the high-dimensional extrinsic features into a lower dimensional space that still captures most or all of the important variation in the data. So the reduced dimensionality manifold of intrinsic behavioral variation embedded in our high-dimensional extrinsic space could be of any kind of shape, but it's often useful to assume that it occupies or is well represented by just a linear subspace of the higher extrinsic feature space. As with previous cases where we've made linear modeling assumptions, doing so allows for relatively simpler and more efficient solutions, and may well be worth the trade-off for missing some of the complexity in some cases. Also, as with previous linear models, in some cases there are ways of extending the model to cope with non-linear modeling problems. So we're going to be talking about projecting our data from its high-dimensional extrinsic space into some lower-dimensional linear subspace. And in order to do that, we'll need to use some tools from linear algebra. So let's just recap a few concepts very briefly because we're going to need them. First of all, recall that the dot product is a kind of similarity metric, and one of the ways of interpreting what it does is that it computes the projection of one vector onto another. So the value that comes out of the dot product, the weighted sum that emerges, can be considered, if you think about it in Pythagorean and trigonometric terms, as computing the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between the two vectors. If one of those two vectors is a unit vector, then the output of the dot product will be exactly the projection of the non-unit vector onto the direction of the unit vector. In other words, it will be the size of the vector in the direction of the unit vector, and we can use this to project a vector from one basis to another. Matrices are just collections of vectors, and matrix multiplication is just a collection of dot products. So we can use a matrix to represent a collection of data vectors, as we've done many times. We can use another matrix to represent a collection of unit basis vectors, and if you multiply those two together, you will wind up with the projection of all of the data into the basis defined by all of the unit vectors in the second matrix. We will, in general, impose the requirement that all of the unit vectors in the basis are orthogonal, that is to say they're all independent of one another. There are cases where it's useful to have bases where that is not true. These are known as overcomplete, but we won't be considering those here. One way to think about the problem that we want to solve is that we want to project our data onto a new basis which captures as much of the variance in the data as possible. If we think about this in terms of projecting just onto one single vector, then the vector that we will project onto will be the one that captures the maximum possible variance in our original data. In other words, it will align with the single direction in our source data where as much as possible of the variation occurs. If we were projecting onto multiple different vectors, so we want to have a basis with multiple dimensions, then the same would be true for the subsequent dimensions, but each time eliminating all of the variance that we've captured in the previous vectors. So the first projective dimension would be the direction of maximum variance in the complete dataset. The second would be the direction of maximum variance in the dataset once the first was removed, and so on. These directions which capture variance in the data are often described as explaining that variance. And these directions are known as the principal components. There's actually a somewhat ambiguous usage here. The term is used both to describe the directions themselves and the projections of the data onto those directions. As an alternative to thinking about capturing the variance in the data, we can analogize with regression. So again, if we're fitting a single dimension to the data, we want to find a line that passes through the data which is the best fit in terms of minimizing all of the errors relative to that direction. So we'd measure the badness of the fit between the whole data set and the single line that we're fitting by projecting all of the data points onto that line and measuring the sum of the squared distances between the projected points and the original data positions. Our loss then would be a sum of squares very similar to the case of ordinary least squares regression. The difference here is that we don't single out particular dimensions, the labeled dimensions, and give them particular importance. Instead, the distances are measured with respect to all of the feature dimensions of the data set. So there'll be the line perpendicular to the fitted line going all the way to the data, rather than being the residual just in the direction of y. The regression way of thinking about it and the variance capture way of thinking about it are, of course, completely equivalent. If the variance doesn't go along the line, then it will go away from the line, and so it will contribute to the loss. So to have the lowest loss, we want as much as possible of the variance to be along the line that we've fitted. It is possible to determine the principal components in exactly this way, by fitting a line at a time, projecting all the data onto that line, subtracting all of those projections from the data, and then repeating the process. However, it turns out that there are more efficient and convenient methods coming out of standard linear algebraic approaches, and these can be described in terms of finding the eigenvectors and eigenvalues of the covariance matrix, or alternatively, although it amounts to the same thing, of finding the singular value decomposition of the data matrix. So just to recap what the covariance matrix is, it's a D by D matrix which tabulates on the main diagonal the variance of each of the feature dimensions, and on the off-diagonal elements the pairwise covariances of different feature dimensions. So how much changes in one correlate with changes in another. This can also be expressed in terms of the expected values of the dimensions like this. If the data happen to be or have been pre-processed to be centered so that they all have a mean of 0, then the covariance matrix can be neatly expressed like this as the transpose of the design matrix multiplied by the design matrix itself, and all divided by the number of samples. If the data have also been standardized, so they all have not only a mean 0 but also a variance of 1, then this actually gives us the correlation matrix. Because of this neat way of expressing the covariance matrix in terms of the data matrix, we almost always use centered data when doing PCA and operations of this kind. This just makes a lot of the maths a bit easier later on. It is possible to do uncentered PCA, but it's less common. In practice, library implementations of PCA will often take care of this for you. So for example, in scikit-learn, the PCA class will automatically center the data and keep track of the means internally so that it can map back into the original data space later when needed. When we multiply a vector by a matrix, this can be viewed as a geometric transformation of that vector. The resulting vector might point anywhere, but in some cases it will point in the same direction as it started, or in completely the opposite direction. As long as the two vectors are collinear, then that counts. In this case, the vector is known as an eigenvector. The vector may change its length in the process, and the proportional change in length is known as the eigenvalue associated with that eigenvector. Eigenvectors are most often expressed as the solutions to this equation. Technically, these are known as right eigenvectors. It's also possible to have left eigenvectors, which are the solutions to this equation. In other words, multiplying by the matrix is the same as multiplying by a scalar, lambda. So if we go back to our definition of the principal components, these are the directions of maximum variance. Let's suppose we only want to capture the first. So we want to find a unit vector, call it u, which captures the maximum amount of the variance in our complete data set X. So for each of the data samples, the data vectors xi in our training set X, the projection onto this direction u will be given by this dot product here, and we'll call that projected value x tilde I. The projection of the whole data set onto this u we'll call capital X tilde, and the variance of the full projected data set is given by this expression here. It's just the sample mean of all of the projected values squared. Bear in mind that we've already centered the data, and so the mean will be 0, and we don't need to worry about it. We can rephrase this in terms of the dot products themselves, so it becomes 1 over n of the sum of u dot xi squared. And we can replace this sum with a matrix multiplication so that it looks like this. So in this case, the matrix product is just computing all of those dot products and then adding them up together. This rearrangement into u transpose x u is just to get everything in the right order so that they add up. But note that the initial scalar factor of 1 over n combined with this x transpose x is exactly our expression for the covariance matrix. So we can substitute that in. So this expression u transpose sigma u is the variance of our complete data set when it's projected onto this vector u. We know that we want to maximize this value, and so that gives us this optimization expression here. Remember that we're imposing the requirement that u is a unit vector. If that's not the case, this expression can be increased arbitrarily just by making u bigger. So this is a constrained optimization problem. We will turn it into an unconstrained one by introducing a Lagrange multiplier, as we've seen before. We can then differentiate this expression with respect to the vector u, which is the thing that we want to choose to maximize the expression, and we get this. We can set this to 0 because we want to find the maximum. We rearrange it and we find that the maximum occurs for this condition here. But this is the property defining an eigenvector. So we know that u must be an eigenvector of the covariance matrix sigma, and the associated eigenvalue will be lambda. We can multiply on the left by u transpose to get our original expression defining the variance. On the right, that gives us lambda u transpose u, but U is a unit vector, so U transpose U, that just gives us the squared magnitude of the vector. For a unit vector, that value is 1, and we can drop it out, which means that the variance of our projection onto this dimension is given directly by the eigenvalue lambda. Therefore, our first principal component is exactly the eigenvector of the covariance matrix that has the largest lambda, because that's the largest variance. We can remove this component from the data and repeat the whole process, and if we do that, we'll find that the second principal component is the eigenvector with the second highest eigenvalue, and so on down through all of the eigenvectors in descending order of their eigenvalues. We can stack the complete decomposition into a matrix U as columns like this, and this can be used to transform the data into the new principal component basis like this. We can alternatively express the same process in terms of the singular value decomposition. So this is a standard decomposition of matrices into 3 distinct matrices that are multiplied together. We'll call those matrices V, D, and U, and the identity for singular value decomposition is that X will equal V times D times U transpose. In this expression, the X is the original data matrix. The V is a matrix whose columns are the eigenvectors of the matrix product X times X transpose. This is an n by n matrix. The D is a diagonal matrix whose elements on the main diagonal are the square roots of the eigenvalues of this same product matrix X transpose. And finally, the matrix U is a matrix whose columns are the eigenvectors of X transpose X. So this is basically just the same as the U that we were dealing with before. If we substitute this decomposition in to the expression from before for calculating the complete projected data matrix in the new principal components basis, we get this. So we start out with x tilde is equal to xu, substitute x, and we get that that is equal to v times d times u transpose times u. But u is an orthogonal matrix. It's a matrix of linearly independent unit vectors. When you multiply that by itself, this factor u transpose u, you just get the identity matrix. And so equivalently, just as x tilde is equal to x times u, it's also equal to v times d. It turns out that there are efficient algorithms for calculating this singular value decomposition, and they can be more numerically stable than the algorithms for calculating the eigenvectors. And so it's quite common to use the singular value decomposition formulation to generate the principal components rather than decomposing the covariance matrix, although both can be done. Either way, the x tilde that we've got out so far, the U matrix or the VD matrix that we've generated, produces a projection with as many dimensions as we had to begin with. We haven't actually done any dimensionality reduction at all. However, typically, each of these dimensions will have diminishing content. That is to say, we're capturing less variance at each stage as you go down through the eigenvectors in decreasing eigenvalue order. To actually reduce the dimensionality, we will throw away, or possibly never calculate in the first place, some of the less interesting lower variance dimensions. Effectively, we can just drop a whole bunch of columns of U and do the projection, and our x tilde will be of lower dimension than the original data space. Typically, there'll be a long tail of principal components that don't have very much going on in them, and so throwing those away doesn't change the nature of the data very much and allows us to keep most of the data variation in a smaller number of dimensions. This can sometimes also be beneficial in terms of signal to noise ratio. If you've got similar noise across all of your dimensions, which may well be the case, that will also be propagated into the new basis, but because we've got more signal in the earlier dimensions, the latter dimensions will have lower signal to noise ratios, and getting rid of them gets rid mostly of noise and less signal. So here are a couple of examples of PCA in action. In this first one, which comes from the Elements of Statistical Learning, the decomposition has been applied to a bunch of images representing the handwritten digit 3. A range of examples of these handwritten digits are shown here. When these are treated as vectors, they are centered, so the mean value of all of the 3 images is subtracted and a PCA is applied to them. You wind up with a series of components representing the directions of maximum variation in the space of handwritten 3s. An example of the first 2 dimensions is shown here. And to see how this relates to variations in the actual images, a selection of the original images is made based on their proximity to percentiles in the spread of values across the first 2 principal components. And that's used to produce this grid here. And we can see that the first component, which is horizontal, seems to capture something about the wideness and roundness of the 3s, and the second component, which is vertical, captures something of the thickness of the stroke of the 3s. Another interesting application of PCA, again in the field of vision, is known as eigenfaces. This work dates from the 1990s, where the PCA is determined from a large number of images of faces. Again, the mean is subtracted and the principal components are determined. And because the principal components are in the same space as images, you can visualize them as images like this. So in this figure, we can see each of the first 9 principal components of the eigenface decomposition, and also below what these look like when they are multiplied by 3 times the standard deviation of each component and added to or subtracted from the mean face image. And you can see that these generated faces definitely have very face-like qualities, and they deal with different kinds of variation in the face. And here we can see an individual face as decomposed against these different principal components. So this output face consists of the mean face plus weighted values associated with each of the different principal components. So PCA is really interesting, it's really useful, and it's used very, very often, in particular as a component in other processes rather than necessarily as a process just in its own right. So, for example, you will often want to apply dimensionality reduction before using some other kind of learning algorithm like an SVM. There are some variations of it. For example, sparse PCA attempts to make the individual principal components sparse. That is to say, to not depend on very many of the input features, to zero out as many of those as are possible. This is done by imposing an L1 regularization on the fitting process. This does mean that the fitting is no longer conveniently captured by simple linear algebraic decomposition, and so it requires a more complex iterative fitting process, and also it's not convex. But the advantage is that the components may be more explanatory. So the components that come out of a standard PCA will typically involve some weighting for all of the different input features. That makes it difficult to interpret them as prioritizing particular input features. If many of the weightings for the components are sparse, then it may make the components themselves more explanatory. Kernel PCA is an application of the kernel methods that we discussed in relation to support vector machines, but applied to principal components analysis. The analysis works very much in a similar way, but instead of acting on the original data matrix, it acts on a matrix of inner products generated through a kernel. There are a couple of fiddly steps to this, but it basically works, and it allows PCA to find non-linear decompositions. One other interesting variant of PCA is known as non-negative matrix factorization. So often with the inputs to PCA, you'll be dealing with physical quantities which have actual meanings and can't just take on any old value. In particular, they often will need to be positive. PCA won't care about that and will quite happily find components that involve negative brightnesses or loudnesses or masses which don't really make sense. Non-negative matrix factorization instead decomposes a matrix into two parts, again, which you can consider as components and combinations of those components representing the data, but the components are constrained to be positive. Again, this requires a more complex iterative optimization procedure, but it can produce very interesting results, which are much more suited to the actual physical problem being considered. So PCA is widely applicable and very widely used. As mentioned, it tends to be used as a processing step in some other learning process rather than just as a learning algorithm in its own right. It has the disadvantage that it can only find linear relationships, but the simplicity of those could also be seen as an advantage, and if necessary, you can introduce kernel methods, for example, to get around that limitation. It's closely related to another matrix decomposition approach, which is known as factor analysis. This uses a very different learning scheme and is based on slightly different assumptions, which means that it is more likely to bring out relationships that are actually of interest rather than just happen to align with the maximum variance. The two are often very similar and actually sometimes confused. Factor analysis is solved by expectation maximization, like we'll talk about next week.